Welcome back. It's been quite some time. Today I want to talk to you about convex and non-convex optimization problems. I want to talk about why we should care about these problems in the first place. I want to talk about the different algorithms we can employ to solve these different types of problems. And I also want to talk about how I've used these algorithms in my own research and how productive each one has been in different types of problem spaces. So, for starters, why should we care about any sort of optimization problem? Well, machine learning and artificial intelligence, the backbone of modern machine learning, artificial intelligence, ChatGPT, Gemini, Llama, whatever model, whatever large language model that you use to generate things, whatever image generation software you use to generate logos or pictures, all of these different models hinge on our ability to train them, right? Training is the process of trying to map a set of inputs to a target set of outputs. In the case of ChatGPT, the input is a prompt, and the target is the output response that you expect ChatGPT to generate. Now that's a stochastic representation, or more of a probabilistic map rather than deterministic, and by deterministic I mean when you give it the same prompt it may generate different responses. Deterministic will generate the same response every single time, but nevertheless our ability to train those models and decrease the error is what leads to better responses. Okay? Convex and non-convex optimization is literally what's going on under the hood of the car. You get into a car, you turn your key, you don't even think about what's going on, right? Hop on ChatGPT, you don't even think about what's going on. You don't even think about the several, probably obscene number of matrix products that are being parallelized to compute your answer right in front of your eyes. But before we even get there, we have to train it. And training it is an optimization problem. So what's happening here? I made this app to help visualize the problem space. It's pretty abstract, but bear with me, I think it's going to make a little bit of sense. So let's talk about this surface that I have in front of me here. Let's suppose that this surface represents error. So x and y are my input, and z is the output. So clearly if z is my error, so suppose it's the error for, say, a large language model like ChatGPT, right? Where do I want to be? Do I want to be on this red point where error is really high? Probably not, right? I want to be all the way down here where error is really low. Now you may say, well, why don't we just look at the bottom of the bowl and pick those x and y points and we'll be done. And that's the parameters that we need for our model. And that's it. And we're done. That is true in this setting, right? We can just pick the x and y down here. We can see it. Boom. Just pick those two. But does ChatGPT only have two parameters, x and y? I'm afraid not, right? That space is so incredibly large that we couldn't possibly visualize it. So what can we do? What hope do we have? If this is our error, right, this is just a representation of the error function, right, so that you can understand visually what's going on. How can we possibly find that lowest point on the surface? Well, what we can do is we can employ these different algorithms. We're going to talk about gradient descent, stochastic gradient descent, and simulated annealing today. And we're going to talk about them in this controlled setting so that even when you can't visualize what's going on in the higher dimensional spaces, when you're training these neural networks, you can at least have an idea algebraically of what's going on in terms of the algebra and calculus, so that you have, like I said, an idea of what's going on under the hood and how learning is actually occurring and why you might not be able to learn in some cases, or why you might have some challenges learning. So what's the deal with gradient descent? Okay, keep in mind, this is a multivariable function. We have x and y as an input and z as the output. Not multivariate, multivariable. Okay? Y is not a function of x. They're strictly orthogonal. Okay? at least in this setting. So gradient descent. x0 is a vector. It's a random starting point. So it's going to be an x and a y, random x and a y. For each iteration t, and we specify the number of iterations we want to do, we're going to compute the gradient. And if your calculus 3 is rusty, all the gradient is a collection of partial derivatives. So you partially differentiate, in this case, with respect to x and with respect to y. It's going to give you a vector. It's going to point in the direction of greatest increase from the initial point. If we're trying to minimize the error, because we want good responses, we want to minimize the error of our responses, right? We're going to step negative that direction, okay? So we're going to compute a new xt. It's going to overwrite the old one. And what we're going to do is we're going to subtract the gradient vector, okay? Keep in mind it's evaluated at the initial point that we're given, right? The previous iteration's point. We're also going to scale it by a learning rate. And this is going to determine how much we should step in each iteration, all right? Remember, linear approximations for nonlinear functions get worse the further away you go from them. So it makes sense that you should have a learning rate that you can scale, some sort of scalar in front of the gradient that you can control. So what's actually going on? If you don't understand the calculus, how can we understand what's going on? Well, this is gradient descent right here. See this path of points? That's literally what's happening. So we start at this green point, and imagine we put a piece of paper up to that green point, a perfectly flat piece of paper. Alpha determines how much we step along that piece of paper, okay? So when alpha is small, like it is right now, 0.1, we're going to step a little bit. If alpha is extremely large, we're going to step a lot of bit, okay? But clearly we want to do this iteratively, because if we stepped a piece of paper right away, all the way down, we would be off the function over here, and we'd be back all the way up here on the z, right? Because we would step in this direction, end up over here. If we made a really large step, we would be back up here, okay? So that's why the learning rate is relatively small in this case, right? And you can see we do this iteratively until we get to the bottom. And that produces the exact same minimum error. So now we have a way of finding the x and y that produce the smallest error, even without knowing what the function looks like. We could literally do this purely algorithmically. I didn't need to visualize this surface in order to find the x and y that give us the smallest error, the one that gets us to the bottom of this surface. This is a convex function. What's the problem, right? What's the problem with this? Well, if every error function was convex, that would be wonderful. We could train it quite easily. It wouldn't be computationally intensive. In most cases, it wouldn't be intractable. You'd literally just employ gradient descent until you get to the bottom and you minimize the error. What's the problem with this? Well, we're going to disregard the idea of overfitting for now. We're going to disregard other concerns in the training process and just talk about the problem with actually training and trying to extract the information that we're looking for from a particular model representation. What's the problem here? Well, we may end up with a non-convex error function. And what a non-convex error function looks like is something like this. Okay. Clearly, we have this start point right here. We do gradient descent, and we end up here at this low point. But is that the lowest low for error that we can get to? No, we could get all the way down here, right? That's a much better representation of the map of inputs to outputs if we can get to down here. But I ran gradient descent from this starting point and I ended up here. How on earth can I get here? Well, I could pick a random starting point, but if I don't have any heuristics to guide me, I'm going to be picking forever. I could literally pick for infinity. There's no guarantee, right? At infinity maybe, but nothing tractable. So what can I do, right? What can I do here? Now, the particularly keen among you may recognize that the z here is actually negative, and error will most likely have some measure of distance, so it'll be squared or absolute valued, so it can't be negative, but bear with me, this is just a representation. Think of it as error shifted down if you have to. But how do we get to here, right? Remember, I can't visualize this function in a higher dimensional space. Algebraically, I need a way to get down here, right? Because I want to find a smaller error between my input and output target. One way, one potential way, I should say, is through stochastic gradient descent. Okay? Stochastic gradient descent is the exact same procedure. Okay? It's the exact same procedure. The only difference is we're adding noise to the gradient. So we're inducing randomness in each gradient step. All right? The scale of the step is still governed by alpha. And if alpha is arbitrarily large, then we can end up searching a lot of the space. Okay, and what I'm going to do is I'm going to show you what this looks like in a convex setting. Looks quite similar, right? Because we're inducing a very small amount of noise, but again, we're still ending up where we should be at the bottom here, right? That's nothing surprising. Let's go on down to the non-convex function here, right? We see a similar thing happen, but what happens when we increase the learning rate, just as an example? Let's see what happens. Not too much, maybe to 0.5. Okay, now we're starting to explore more of the space. So instead of just diving right down into the local minimum, we started to explore up a little bit. Keep in mind, this is stochastic. Every time I run this, it's going to be different. I'll increase alpha to 0.7. We're exploring significantly more of this space now before we get to this local minimum here. What happens if I make it 0.88? Now we're exploring a significantly larger portion of this space, right? So this is quite interesting, and perhaps there is a way that we can extend this. Maybe if we have an arbitrarily high learning rate, we can keep a hash map of all the parameters and the corresponding errors and just pick the parameter set that yields the lowest error. But that's going to be pretty similar to the idea of simulated annealing. So we're going to get there in a moment. But just for illustration purposes, here it is with a learning rate of almost 1 from the same starting point. Okay. So that's exactly what's going on. Now, what about with this convex sort of representation here, right? Let's scroll back up to this convex representation. You can see that it's essentially just noise, right? We're going back and forth. It's pretty much just inducing random noise in the gradient. We're going to continue to step back and forth in that fashion. Okay, so clearly the learning rate is a hyperparameter that has to be tuned to the problem. Okay, so stochastic gradient descent is one way to get over potential local minimums, right? Because if you are, let's say, sitting at the top of a hill, right? Let's say we're sitting at the top of this hill. If we compute the gradient, maybe we're going to step in this direction, right? That would be great. We would end up all the way down here. But maybe if we just compute it vanilla, we start going this direction. If we induce noise at the top here, then we have a probability greater than 0 of stepping in this direction. Okay, depending on how large the noise is, it's going to depend on the probability. It's going to change the probability of ending up actually at this global minimum down here. All right, so stochastic gradient descent is more of a probabilistic version of gradient descent in a way. We have no ability really to control what's going on because, again, it's a probabilistic algorithm, or not probabilistic, but it's a stochastic algorithm. But we do have the ability to potentially overcome these local minimums. Is there anything else we could do? I want to talk about one last one that's been particularly productive for me, and that is simulated annealing. I find it fascinating as an algorithm. Simulated annealing, we take a initial starting point, again it's still a vector, and we have some temperature T. And essentially what we're going to do is we are going to generate a random point in the neighborhood of our current point. We are going to compute a change in functional value, and if the change in functional value at that new point is less, then we're going to step there with certainty. If it's greater, then we are going to step there with a probability that's governed by the change and the temperature. And one way to interpret this is that as the temperature is high, we're bouncing around a lot, right? But then as the temperature starts to cool off, we're not bouncing around as much, all right? So it's pretty sweet. It's a pretty cool algorithm, right? And if I was to say increase the number of iterations here, let's make it pretty big. Let's make it like 100. And then see if we could see the start, the end. Check out some of these local extrema. So we started at the same point here. Whoops, let me scroll down. So we started at the same green point. We run 100 iterations of simulated annealing. And all of these blue points represent minimums that we've observed. Or I guess this is nodes along the last path that we've observed, or the optimal path. Yeah. So we observe 100 different minimums per iteration. You can see, compared to stochastic gradient descent and gradient descent, we actually end up at the global minimum. So this is quite interesting because we explored a significantly large fraction of the space just by doing this a little bit differently. We didn't use any calculus. Instead, we did a probabilistic search where essentially we are balancing exploration and exploitation based on our temperature and our cooling rate. So for example, if I was to decrease this temperature right off the bat, right, let's make the temperature 1. Will we explore more of the space? No. We actually get very similar results, if not the same minimum, as stochastic gradient descent and gradient descent, or at least stochastic gradient descent with a low learning rate. But if we make temperature very large, then we explore much more of the space, right? So here we end up at this minimum right here. Okay, we actually don't end up at this global minimum down here, but we end up at this minimum right here. And if we change the cooling rate, maybe we cool at a lower rate, we get to a different one. So this is just a different type of optimization algorithm. Again, it's quite interesting. So essentially, instead of updating the gradient with, or instead of updating the initial starting point with the gradient times the learning rate, or the gradient plus noise times the learning rate, this is the functional representation. We say update it as x prime if delta E is less than 0. So if the functional change is less than 0, we update it in that direction. Otherwise, with probability, exponential negative delta E over t, if delta E is greater than 0. So with some probability greater than 0, we are going to explore a non-optimal step. And then if we don't hit, then we are going to just go with the original point and choose a new random point and then do it again. And that's why we have 100 iterations here. And that is how simulated annealing works. So it's more of a search algorithm, really. And it can be used in a machine learning context. It can also be used in other types of search problems as well. So it's quite interesting. So those are the 3 algorithms I wanted to talk about today. There are different flavors of each that you can use. So you can use simulated annealing in the context of stochastic gradient descent. Perhaps you even have some temperature and cooling rate for your noise, and you scale it in that capacity. Then maybe you have a probabilistic rate of acceptance. There's, really just an infinite number of ways that you could possibly establish these optimization algorithms. But these are a couple of different flavors, and they're quite interesting. So I've actually had a lot of luck employing simulated annealing in the context of training variational autoencoders to learn arbitrage-free volatility surfaces. It actually preserved the arbitrage-free nature of the surface even when generating from the latent space a brand new volatility surface. And that was quite useful in approximating pricing functionals using neural networks, essentially, to learn the parameter set of a model to a volatility surface. It allowed us to use significantly more data. So simulated annealing in conjunction with stochastic gradient descent and other different optimizers, like other routines like Atom, very, very productive. That combination of having like a sort of a simulated annealing style learning rate was extremely effective in sort of surpassing and overcoming those issues of getting stuck at a local minimum, because really that's what was happening most of the time. Is, we were trying to learn some sort of optimal representation. We wanted to be down here, we would get stuck like right here, and the generated surfaces just wouldn't be any good. But eventually we were able to learn really great representation of those surfaces, and it was thanks to a combination of, like I said, the simulated annealing style training with gradient descent. So that's going to do it for this video. I hope you enjoyed. I just wanted to go over a couple of different algorithms in the context of deep learning, machine learning, neural network training, the problem space of really artificial intelligence in general, and different ways that we can start to think about how these models are kind of built, what's going on under the hood. Because more and more every day I'm seeing adults, children alike using ChatGPT, Gemini, Llama, maybe less Gemini and Llama, but you get the gist that everyone seems to be using artificial intelligence, but there isn't really a understanding about what's going on in the training process. This has nothing to even do with the reinforcement learning or human feedback with the reinforcement learning. We talked nothing about different types of learning structures, right? There's supervised and unsupervised reinforcement learning, and there's also a reinforcement learning component as well. So this is kind of just the tip of the iceberg here before we even start to get into more sophisticated training methodology. So I hope you enjoyed. I hope this hopefully was enlightening to see how essentially machines learn in the context of a 3D visualization of error, right? We want to get to the lowest point, and there are different algorithms that we can use to get to that lowest point. So feel free to leave a comment if you have any questions. You can always reach out to me. I'll leave a link to this app in the description below. Otherwise, I will see you in the next one.